Hello and welcome to the Cisco ACI Field Engineer Implementation class. My name is Matthew Taylor and I will be your instructor for this module. The agenda of this course in the beginning of the FEI class are very basic. What are we solving? What are the typical problems that we would see in implementing a network infrastructure that we want to resolve by using software tools? Also, we will go over virtual extensible LAN basics, or VXLAN, for those who are not familiar with VXLAN. We will go over ACI fabric fundamentals. We will go over as well fabric forwarding, endpoint learning and lookup, and fabric innovations in the ACI fabric. So the question comes down to, what are we actually physically solving? So I think that it's fair to say that we use VLANs and IP subnets as policy boundaries. Think about it like this: access control lists, quality of services, load balancing, among others. VLANs have a lot of local significance. So when you usually tend to define a VLAN, it is usually associated with an IP address, which could automatically imply some security policy or load balancer, what have you, because of the way that we use IPs. We tend to live in layer 3, not in layer 2 or layer 1 from that perspective, is usually when we end. An IP address can represent an identity, a subnet, or an access control list entry. Now, what is it? Usually from a network perspective, a VLAN is always tied to a subnet. So you're always going to have VLAN 40 is going to be, and let's just say use 172.16, 172.16.40. That's usually the way that that we've been taught to map subnets to VLANs. So all those things tied together actually brings this presentation forward. The VLAN represents a subnet. But the trouble is that can actually not really allow you to implement the original intent of the OSI model. The OSI model is actually created so that these services can be portable throughout each layer of the stack. When we tie a VLAN to a subnet, we're actually locally making that locally significant to that switch, to that port, to that IP address. So we are stateful from that perspective. We're not stateless. So as we can actually say, our basic network policy constructs, those are the SLAs and the layer 4 through layer 7 services. These are all virtual constructs, but they're tied to a stateful model. So we want to try and get away from that stateful model. So when we actually talk about the language between developers and infrastructure teams, okay, developer teams and infrastructure teams speak different languages. Developers talk about a provider-consumer relationship where the application is consuming traffic from a database, or a web tier is actually consuming information from an application layer. So those group of components will provide a function which is consumed by another group. Network teams must translate the developer's vernacular into VLANs, subnets, switch port settings. Network teams care about ports and protocols. So there's not much awareness on their part of the devices that are actually touching the network. So ACI is bridging that gap by providing a host-centric fabric. ACI attempts to shrink the time frame from application development to QA and then to implementation and production. So as you can see here, developers talk about application tiers and provider-consumer relationships, whereas infrastructure teams are actually looking at the physical construction. So we're trying to bridge those two gaps together. So we do talk different languages. Let's make sense, right? So our old school type configuration for a switch, what do we have to do if we want a VPC two switches together? We connect them together. We do a VPC peer link. We create a VPC domain. We put the ports in those in that VPC domain. And then we go in and we IP the port on a whatever subnet that we want to physically do. Then we tie that to an interface. We create a VRF. So we also enable features, and then we enable layer 3. So all this is done at a command line via conft, as we've all done before. We've all done this. So ACI is trying to, and actually does a very good job at resolving those network constructs into a policy-based model. This is this is where we're actually going. Okay. In order to control a packet through the data center, this is the configurations that we have to look at, right? We have initial switch configurations. You can see that from the cloud we have switches and the router configurations. Of course, how many switches depends on your topology. We also have a firewall configured where we have an administrator configure various filters. Another admin configures virtual IPs on the load balancers and also adding in additional features like SSL offload. So there's a lot to be done on a lot of different devices to control application traffic. This is not what an application developer sees. An application developer sees, oh, I have an application and I have a web tier and I have a database tier. But there's a lot that has to go on behind the scenes. So they do not grasp the magnitude of the process. So what we have to do is we have to translate this to a policy-based software-defined model to where we can replicate this configuration and begin to actually make provisioning the network from stateful model into a stateless model. So it's a manual-intensive box-by-box process. You can see this when you consider change management. How many entities are involved? If I need to make configuration switches on switch 1 and 2, how does that affect the load balancer or the firewalls? How does that affect the router, right? So when you consider change management, you have to consider other entities. So it's typical to have multiple admins involved in any change process. If adding a VLAN, if you wanted to add a VLAN, it's a relatively simple process, but in an effort to stay compliant, corporate change management procedures may dictate approval from several administrators. So what does this do? We've all been through this. It extends your implementation time for deployment. So the prevailing sentiment is the network is too slow, takes too long to get things set up and deployed. But the trouble is that it's a manually intensive process that's error prone, and we usually do not get the time to actually make those changes. So this is what we are resolving with ACI. ACI does do things differently. Okay, so you can see there's lots of boxes here, and we will go through these boxes in this class. Okay, suffice it to say that from a policy model, you construct it at the policy layer and then deploy it to the actual physical switch layer. So we will go through all of these individual boxes as we go in this class, but ACI abstracts those concepts and then allows you to deploy them as policies to the local switches. So ACI abstracts the network. So first of all, the first thing that you need to do is you need to actually think about ACI as, if you want to think about this from a core aggregation access layer, you need to think about this as a collapsed access layer and aggregation layer. Okay, so our ACI abstracts the physical from the logical. So what do we actually mean by that? The switches are basically waiting for instructions from a control plane, in this case the APIC. So the switches have no configuration on them. Can you actually put a configuration on an ACI enabled mode 9K switch? No, you can't. The APIC has to provide that policy construct. You can certainly do it in a 9K standalone. So ACI abstracts the physical from the logical. So in the concrete model that we have at the top, you have switch nodes, which are your leaves and spines. You have your interfaces, your local interfaces, and your VLANs. Now, I want you to begin to think about VLANs as a non-physically tied VLAN to subnet ID. VLANs are going to be, there is a role for locally significant VLANs in ACI. It's not going to be from a hypervisor perspective, But it would be if you're extending layer 2 into the network, or you're doing something like if you're doing SVIs in layer 3, what have you. But I want you to get it from a hypervisor perspective that VLANs are not going to be as locally significant as you would actually think about them today. Now, the logical model actually extends this down. So concrete model is just the switches. That's all that is. Now, the logical model is the logical constructs that allow us to deploy an entire application stack to the physical network. So what do we have here? We have tenants, which are a container for common applications, groups, or services. It can be anything you want them to be, really. Some customers will have one tenant, some will have plenty, more than one. Doesn't really matter. You have VRFs, virtual route forwarding constructs, which are deployed amongst the entire fabric. You have bridge domains. But the key thing to ACI, since ACI is a whitelist policy model, traffic is automatically denied through ACI. So what you have to do is you have to actually think about it, begin to change your mind about thinking about ACLs that allow for traffic, or actually from an ACL perspective in the traditional blacklist model, you're actually denying or you're actually denying traffic. In a whitelist model, you're allowing traffic. So contracts allow traffic to flow between two endpoint groups or endpoints. Now, all an endpoint group is a physical endpoint device. That could be a physical server. That could be a port group on a distributed virtual switch. Okay, that's all they are. Now, under the logical model as well, we have QoS, we have filters, and we have firewalls as well. So the contract takes those policies that we would usually put in an ACL, quality of service, stuff like that, and puts it in the contract perspective under subjects and filters. So ACI is one big switch. So if you were to think about this from a 7K architecture, a ACI switch, the spines are the fabric modules. So this is a leaf spine topology. It's an old topology that's been around for years and years and years. Old telco stuff. Because it works. It provides multiple links and provides a common, consistent, latency-defined fabric. May or may not have been the exact perfect way to say it, but it is early in the morning and I've only had one cup of coffee. But you have a consistent number of links, consistent bandwidth, and consistent latency. So in the spines resemble fabric modules that you would have in a 7K on the backplane of a 7K for the line modules to communicate between themselves. And then the leaves represent line cards. So think about it as a split out 7K switch. So when we begin to think about stateless networking, I've taught UCS for 10 years. UCS is very, very, now I'm starting to go south. UCS is the extension of the server identity to a physical server. So really UCS is a stateless model as well. I define everything that I want that server to be in UCS Manager, and I deploy that down to a blade. This is the same thing from an application profile in ACI. So what does that mean? An application profile is basically my 3-tier application. Could be database, could be app, could be web and database, it could be app and database. Doesn't really matter, right? It's the collection of all application endpoints in the endpoint group, plus any layer 4 through layer 7 service graphs. When we talk about layer 4 through layer 7 services, we'll talk about how we do that integration later. And it also has the rules or the contracts defining the endpoint connectivity. Contracts will allow us to allow traffic between EPGs. Permit is always going to be default. So when you apply a contract, you are permitting that specific traffic to flow between these endpoint groups. Now, when you actually put in a deny, that means you're in essence setting up a blacklist model, so that would actually be called a taboo contract. But an application profile is the logical container that would contain all of those entities and policies that will then get pushed down to the actual switches themselves. And it's stored in XML or a JSON schema. Honestly, to me, XML's easier to read, but I'll actually show you how you can actually find the URLs later on and actually deploy them on the fabric, using Postman. So when we take a look at the APIC rendering policy, switch nodes are stateless. So we have the ability to populate the ASICs on an as-needed basis. There's no saved configuration on the switch platforms. The only thing that connects to spines is leaves. So leaves connect to spines, spine connect to leaves. Nope. Okay, so there's always an exception to every rule, but generally, unless you're doing multi-pod or multi-site, there's no need to connect anything other than a leaf to a spine switch. Okay. Generally, our overlays are going to allow us to treat IP addresses differently. So either identity for a server, location, a VLAN, or a filter in the access control list. The application policy model defines the application requirements. Then the APIC instantiates the policy on each device. So each device will instantiate the required changes based on the policies. Now there are some. A bridge domain will be automatically available via SVI to all points on the fabric itself, but that physical switch is going to need to have an individual switch profile for connectivity, since it will actually connect to individual switch ports. All forwarding in the fabric is managed through the application profile. So IP addresses are fully portable anywhere within the fabric. Security and forwarding are fully decoupled from any physical or virtual network attributes. And the devices autonomously update the state of the network based on the configured policy requirements. Okay, so basically, everything that requires the application to run from a logical perspective is in the application policy, and then that policy is then converted into the logical and physical configurations that the switch would need to operate as a normal switch. And that is done at the APIC. And as you can actually see, we've actually deployed virtual machines. We've deployed our application profiles. So here's our virtual machines spinning up. Our load balancer is connected to our leaf switch. And we can move them. They are fully portable within the fabric. So of course, this actually now this is actually showing a distributed virtual switch, right? So we can move virtual machines from host to host on the same DVS. But you can actually see how that whole policy follows the virtual machine. It follows the port group because it's managed by ACI. So when we apply a policy to an endpoint, so the endpoint is the physical device that attaches to the fabric. So let's say we were actually talking about virtual machines. So this would be a distributed virtual switch. The APIC will detect the endpoint and derive the source EPG, and then the APIC will push the required policy to the actual leaf switch. Now, there's two different ways this can actually happen. Okay, so you'll actually create the application profile, you'll create everything, but then you will apply the EPG. You will bind an EPG to, in this case, a VMM domain. But you have to decide how you want to actually set those up. Okay, you can push a policy based on resolution immediacy or instrumentation immediacy. So there's a couple of different things that we have to think about here. Resolution immediacy is going to be at the APIC level. So depending, pre-provision, the policies are pushed to every leaf node with a port associated with the VMM domain. Immediate, the policies pushed to the leaf node upon the hypervisor physical NIC attachment to the VDS. And on demand, the policies are only pushed to leaf node upon the hypervisor attachment to a distributed virtual switch and VM assigned to the port group. So these are all very, very, very easy to do. Pre-provision means as soon as I actually associate a port with the VMM domain, it'll push the policies over. So it'll push the port groups down to vCenter. Immediate, it will do it as soon as I connect a physical NIC to my distributed virtual switch. Or on demand, it will only push the leaf node when I assign a VM to that port group, is when it will actually push that policy down. Now, resolution immediacy covers APIC file system storage space, which is a lot cheaper than actual TCAM space. If you go under here in the leaf node hardware, if you choose immediate, the policies are programmed in the policy CAM table as soon as they're received, or on demand, their policies are programmed in policy CAM only when the first packet is received through the data path. Okay, so under instrumentation immediacy, it's deployed immediately to the leaf node itself. Now, if you don't have a lot of EPGs and a lot of contracts and a lot of complexity, you could do that. But understanding that your TCAM space is a lot more expensive on a leaf switch than it is as a file system on a physical APIC. So ACI decouples the endpoint ID. Okay, so if we actually think about this, frames entering the fabric can be a native Ethernet frame, .1Q tagged frame, a VXLAN encapsulated packet. At egress, the fabric can leave the same endcap or endcap as something else, which is called normalization. Every leaf can also be a default gateway. ACI is an object-based model, so it's different from NXOS. The switches running in ACI mode are only programmable via an object-based policy engine operating in the APIC controller. So the controller becomes an integrated part of the network and holds the profiles containing the policies for programming the switches centrally. The switches themselves do not hold a CLI configuration file. All that configuration is in the APIC and is actually pushed down. So it's an object-oriented written in XML or JSON. So the policy consists of application-centric information for connectivity, L1 through L3 IDs and L2 or L4 through L7 services. So in this specific instance, in a two-tier spine and leaf topology, with a leaf spine network, every server on the network is exactly the same distance away from all of the servers. 3 port hops. So I'm the same exact distance no matter where I am. The leaf switches provide external connectivity onto the fabric. So if you have layer 3 outs or a layer 2 extensions or layer 4 through layer 7 services, you will connect those at the leaf level. You will not connect them at the spine level. So of course, there's multiple for 10 gig, 40 gig, as well as 100 gig, and also 400 gig as well. Leaf switches are the policy enforcement points. Spine switches, remember, they're just fabric modules. They're 40 gig switches, 100 gig switches. They do not do policy enforcement. The APIC controllers are the centralized point of management for managing the fabric configuration and observing the summary operational state. So it has a distributed framework across a cluster of appliances. So generally there's 3. From a policy perspective, the APIC is the primary point of contact for the configuration and acts as the policy repository. So external connectivity is, of course, handled through the leaf switches, and service nodes are physical or virtual appliances. They can provide specialized network functionality that traditional bridging and routing network elements do not or cannot provide. So examples would be stateful firewalls, load balancers, NAT gateways, etc. Now, what we have to think about as well is that it's a distributed layer 2 gateway. We're also removing all flooding requirements for the IP control plane. So there's no ARP or GARP traffic. That's actually reversed in ACI. Supports standard bridging routing semantics, supports VXLAN, which is most important, as well as 802.1q. So what actually happens when we're sharing services in ACI? You can see here that we have providing consuming EPGs, can be in a different layer 3 context, route leaking, is configured automatically between tenants. So you can actually see from a shared services perspective, if we needed to share services between DNS and DHCP, we can provide that through an AD contract and then allow for app servers and web to consume those specific services. But how does that actually happen? So again, Cisco's reusing an old, well, not old, but let's just say, not young, routing protocol called ISIS, intermediate system to intermediate system. It's a two-level hierarchy of routing. So you can have multiple level 1 areas interconnected by contiguous level 2 backbone, leaves, and spines. A router can belong to level 1 or level 2 or both. So the linked state database contains information about that area only, the level 1. The level 2 linked state database contains information about that level as well as each of the level 1 areas. A level 1 and level 2 router contains both level 1 and level 2 databases. So basically, it just advertises between intermediate system to intermediate system. Route leaking can help reduce suboptimal routing by providing a mechanism for leaking or redistributing level 2 information into level 1 areas. So by having more detail about inter-area routes, a level 1 router is able to make a better choice with regards to which level 1 or level 2 router to forward the packet. So what we're actually deciding is what is the best route, what is the fastest route to actually get our traffic out of the fabric, and that's determined by ISIS, and it's determined at the physical spine level. Here we see an overview of a typical 3-tier application. As data comes from the outside, we filter it, apply some quals before sending it to the web tier. Similarly, this occurs as the data flows to the app tier, apply quals parameters there. And then services. With ACI, we can build the relationship between these objects at the network level. So you can actually see that we actually build all of this physical constructs, and we can actually also monitor the entire application and get an application health score. So the APIC actually monitors the per hop visibility on VXLAN, both physical and virtual constructs are actually monitored individually and scored at the APIC level. So the APIC becomes not only your provisioning tool, but your management tool as well. So now we talk about what makes software-defined networking different than what we would actually use for standard physical networking constructs. And that's VXLAN. So VXLAN is the choice overlay. It's a layer 2 overlay running over a layer 3 network and addresses several pain points that exist in traditional networks. What's the biggest pain point? 4,000 VLANs on a port. So data center applications tend to have a very simple view of the world. They often require layer 2 adjacency among an associated group of end devices. This necessitates figuring out how to stretch layer 2 domains across the data center to scale without breaking layer 2 adjacency requirements. If you want to think about it this way, virtual machine workload mobility and some clustering apps must communicate over a dedicated VLAN or subnet and cannot be routed. So what you would do is you would do a layer 2 VXLAN encapsulation with MAC address and MAC address. So when a virtual machine sends a packet, it's encapsulated into another outer MAC header with a 24-bit segment identifier. What usually happens though is that, one, you're doing poor link utilization through a port channel if the traffic is hashed to a single link, which is generally what happens. And the technique is restricted to a single layer, layer 2. Hence, you cannot migrate workloads to pods separated by a layer 3 network. So in addition to layer 2 adjacency issues, building large layer 2 segments creates large broadcast domains and increases the scope of undesirable events such as spanning tree reconvergence. Additionally, VLANs can only scale to a maximum of 4,094 segments, with many VLANs reserved by the switch for internal use. So Cisco, in partnership with other vendors, created VXLAN standard to IETF as a solution, for data center network challenges. VXLAN is designed to provide the same Ethernet Layer 2 network services as VLAN does today, but with greater extensibility and flexibility. So the VXLAN standard provides for elastic workload placement and higher scalability. So, of course, you can scale to 16 million VXLAN segments. The Nexus 9000 switches are designed with hardware-based VXLAN function. So basically, we create the policy model, the APIC, and the leaf switches in this case does all the VXLAN encapsulation, okay, in hardware. So that's easy integration between VXLAN and non-VXLAN infrastructures. They both speak the same language. Deployed as a VXLAN gateway, the 9000 switches easily connect VXLAN and classic VLAN segments, so they both talk the same language. If you were to compare VLAN and VXLAN, VXLAN offers the following benefits. You can flexibly place multi-tenant segments throughout the data center, because instead of a VLAN encapsulation, you have a VXLAN encapsulation, which gives you more granular data in the actual packet itself. Higher scalability. VLAN uses a 12-bit VLAN ID to address Layer 2 segments. VXLAN uses a 24-bit segment ID, known as the VNID. VXLAN network identifier, which enables up to 16 million VXLAN segments to coexist in the same administrative domain. Better utilization of available network paths in the underlying infrastructure. VLAN uses spanning tree. In contrast, VXLAN packets are transferred through the underlying network based on Layer 3 header and can take advantage of Layer 3 routing and ECMP routing, and link aggregation to use all available paths. VXLAN can be implemented both on hypervisor-based virtual switches to allow scalable, repeatable virtual machine deployments, and on physical switches acting as gateways to bridge VXLAN segments back to VLAN segments. So we're taking the advantages of VXLAN and still allowing us to replicate what we do in our old environment from a VLAN perspective. So a VXLAN encapsulation defines a MAC in UDP encapsulation scheme, where the original Layer 2 frame has a VXLAN header added and then placed in a UDP IP packet. With this MAC in UDP encapsulation, VXLAN tunnels Layer 2 traffic over a Layer 3 network. So this is how it actually does this, right? So you have a VXLAN packet. So that 8-byte VXLAN header consists of a 24-bit VXLAN instance ID, or VNID, and it has a few reserved bits here. But the VXLAN header, together with the original Ethernet frame, goes into a UDP payload. The 24-bit virtual network ID allows VXLAN to support 16 million LAN segments. It's also an approach to building a multi-tenant data center by decoupling tenant Layer 2 networks from the shared transport network. The ACI VXLAN VNID is used as a tag to identify forwarding information based on the ingress and egress nodes. The VRF, context, the packet it's a member of, the bridge domain the packet should be forwarded on, and the EPG, the frame that it is sourced from. So EPG, bridge domain, VRF, and tenant as well. Layer 3 VNIDs are used to transport inter-subnet tenant traffic. In the ACI model, traffic that arrives at the fabric ingress that is sent to the ACI fabric default gateway is routed into a virtual network segment known as a Layer 3 VNID. A single Layer 3 VNID is associated for each tenant context. The ingress leaf node will send the VNID. The egress leaf node will use the VNID to perform local forwarding lookup. The APIC controls the allocation of VNID labels across the fabric. The Layer 3 VNID is allocated by the APIC, and then the traffic that goes across the fabric is transported using the VNID of the Layer 3 segment. In the egress leaf switch, the packet is routed from the Layer 3 segment VNID to the VNID of the egress subnet. The ACI model provides a much more efficient forwarding in the fabric for the traffic that's routed within the tenant. With this model, the traffic belongs to the two virtual machines belong to the same tenant on the same physical host but on different subnets. So the traffic travels only to the ingress switch before it is routed using minimal path calls to the correct destination. In current VM environments, the traffic travels to an edge VM, possibly on a different physical server. Therefore, it is routed to the correct destination. So you can actually see that we're only really talking about the VXLAN ID of the 24 bits. You've got the original Ethernet packet over on the right-hand side, and on the left-hand side we have our VXLAN encapsulation. So a couple things. This is a very busy slide as well, but really we should only be looking at the dynamic rate estimator. So that's how we measure congestion and latency in the fabric. So you've got that DRE flag, and you can actually see it will actually show if there's specific load in the fabric. The DP and SP flags are employed to determine when or where policy is applied. So we'll talk about that policy identification later on, but here's some additional ACI VXLAN header details that are actually done, and it's kind of the secret sauce of ACI. What do we really need to troubleshoot this from a header perspective? Chances are not. We will be doing more configuration at the application profile layer than what we will with a VXLAN headers. So the VXLAN tunnel endpoint, how does VXLAN work? We extend the layer 2 networks across the layer 3 infrastructure using MAC over UDP. So here we have each actual device has a VTEP or a virtual tunnel endpoint. It can be a switch interface on the local LAN segment, an IP interface to the infrastructure VLAN, and it will usually have the following functions. Every single device, a leaf, a spine, a layer 2, layer 3, whatever, any EPG is going to actually have a VTEP assignment. So the switching takes place between VTEP to VTEP. Cisco Nexus 9000 VTEPs have two types of logical interfaces involved in the VXLAN. You've got the switch interface, which is the local LAN segment to support endpoint communication through bridging. Then you have the layer 3 IP interface. That's the transport IP with a unique IP address. And that is in Cisco ACI. The transport network is the infrastructure VLAN. The layer 3 IP interface is referred as a network virtualization edge in ACI and is bound to a loopback. So the NVE IP has several functions. It uniquely identifies each VTEP on the transport network on the infrastructure VLAN. It does the encapsulation and de-encapsulation of VXLAN frames. It discovers remote VTEPs and switches for its configured VLAN segments and learns remote MAC to VTEP settings to be used for forwarding lookups. And again, this is the network virtualization edge. It is actually distributed amongst the fabric and assists basically the spines to know all of the physical endpoints. And then the spines have their own table for updating and forwarding that data out. So VXLAN segments are independent of the underlying network topology. So we don't care what those VTEP IP addresses are. We create them as a pool when we first build ACI and as the initial fabric setup. It's transparent to us, but it's important from an infrastructure perspective. So it routes the encapsulated packets based on the outer IP address header. So you have an initiating VTEP as the source IP and the terminating VTEP as the destination IP address. So source and destinations are used to forward the VXLAN encapsulated traffic through the transport network, the infrastructure VLAN. The APIC itself will discover the switch topology, then assign IP addresses to each node, leaf and spine switches, to be used as VTEPs. And VXLAN is the sole transport between leaf and spine across the fabric. VTEP functionality can be implemented in software such as a virtual switch or in the form of a physical switch. So when it's acting specifically as a hardware gateway, the 9000 VTEPs combine a VXLAN segment and a classic VLAN segment into one common layer 2 domain. So the ACI fabric uses VTEPs for many things. A vSwitch could be a virtual switch, could be a 5K supporting VXLAN. A VTEP device could also discover remote VTEPs for its VXLAN segments and learn remote MAC to VTEP mappings through its IP interface. So what actually happens are VTEP devices, how they're employed in the fabric. There's infrastructure loopback IPs for the spine and leaves. You've got node level communication with the APIC, termination endpoints on the top of rack switch, peering for BGP diagnostics. There's also leaf loopback TEP IP addresses, and that will actually address the logical VTEP shared between VPC peers. The leaf loopback fabric TEP IP addresses, they are for VTEP addresses used to communicate to downstream vSwitch VTEPs. Identical across all leaves to allow downstream mobility of VTEP devices. Then you've got the spine loopback proxy Anycast IP addresses. So the loopback proxy Anycast IP addresses are how actual traffic is distributed amongst the fabric, how the spines actually learn where all the endpoints are, because not all leaves will know all endpoints in the fabric. The spines know all of the actual endpoints in the fabric. So each fabric proxy redundancy group will share a common Anycast address. ACI fabric fundamentals. In this session, we'll talk about encapsulation, normalization, decoupled identity and location, and policy identification and enforcement. So traffic is, of course, within the fabric is encapsulated as VXLAN by default. External VLAN and VXLAN and or NVGRE tags are mapped at ingress to an internal VXLAN tag. So what we're actually illustrating here is an encapsulation normalization. So forwarding is not limited to or constrained by the encapsulation type or encapsulation of the overlay network. The external identifiers are localized to the leaf or leaf port, which allows reuse or translation if required. A bridge domain forwarding policy can be defined to provide standard VLAN behavior where required. Now that's actually talking about network-centric mode. So any external identifier is actually distinguished differently from application endpoints, but it is still translated into the internal VXLAN tagging format. So external identifiers are localized to specific leaf or leaf port. So you can actually see here that we've got an 802.1q on VLAN 10 or an NVGRE with with a virtual ID of 7456. Those are both tagged individually on the border leaves. So again, Cisco ACI is a simple two-tiered leaf spine architecture which provides efficiency, resiliency, and predictability. Everything between the leaf and spine is an infrastructure space and the infrastructure tenant. There's not that much you can do in this space unless you want to do multi-pod or multi-site. The ACI fabric enables any service, physical or virtual, anywhere with no need for additional software or hardware gateways to connect between the physical and virtual services. It also normalizes encapsulation for VXLAN and VLAN in hardware. So the ACI fabric decouples the tenant endpoint address, its identifier, which of course is its VNID, from the location of the endpoint that is defined by its VXLAN tunnel endpoint, its VTEP address. So forwarding within the fabric is between VTEPs, VTEP to VTEP, virtual machine to virtual machine, but from a fabric perspective, it's VTEP to VTEP. The mapping of the internal tenant MAC or IP address to a location is performed by VTEP using a distributed mapping databases maintained in the spine. Now, locally significant, if you have two virtual machines connected to the same leaf, the leaf will actually switch that traffic. There's no need to go up to the spine. But when virtual machines are connected to hosts that are on separate leaf switches, then yes, the spine proxy will come in and he will know where to forward that traffic to. So the ACI fabric decouples endpoint identity, location, and associated policy. So the underlying topology of VXLAN is still running, but it's independent. We've actually set the policy at the API level and pushed the policy down. There's full normalization of ingress encapsulation. for 802.1q, VLAN, VXLAN. There's a distributed layer 3 gateway for ensuring optimal forwarding for layers 2 and 3. Support for standard bridging and routing semantics without standard location constraints. You can also insert services and redirection, and removal of flooding requirements for IP control plane for ARP, GARP, DHCP, and unknown unicast. So remember, this is a VTEP to VTEP switching mechanism via our VXLAN VNID, our 24-bit address. So as you can see, the virtual machine moves, VTEP is going to get updated. So routing within a tenant, if we were to actually take a look at the independent forwarding, either layer 2 or layer 3, they're supported without changes to applications or endpoint stacks. Remember, those are totally disassociated from the physical constructs of the network itself. So no longer do we have to map the application layer to the physical layer on the switches themselves. The fabric will provide a pervasive SVI. Okay, let's actually go a little bit differently here. So the fabric provides a tenant default gateway functionality. So for each tenant, the fabric provides a virtual default gateway. It's a pervasive SVI that spans all the leaf switches to which the tenant connects at the ingress interface of the first leaf switch that is connected to the endpoint. Each ingress interface supports the default gateway interface, and all of the ingress interfaces across the fabric share the same router IP address and MAC address for any given tenant. So in ACI, layer 2 and layer 3 forwarding semantics are supported without changes to applications or endpoint IP stacks. ACI will forward layer 2 and layer 3 traffic directly to the destination endpoint. So it's kind of like a distributed layer 2 switch, one big giant switch. Bridge semantics are preserved for intra-subnet traffic. There's no time to life decrement, no MAC header rewrite. The ACI fabric will learn the MAC for non-IP packets and learn the IP address for all other packets. So in an example, leaf 3 is performing local switching between 10.1.3.12 to 10.6.3.2. The IP addresses do not matter because the endpoint is decoupled. And also, from this perspective, since we're talking about virtual machines, the VLAN tags are not significant either. And we'll talk about that more as well. But it's a distributed default gateway amongst all switches in the fabric. So when we talk about packet forwarding, VXLAN uses stateless tunnels between VTEPs to transmit traffic of the overlay layer 2 network through the layer 3 transport network. So the spine is used as a backplane or midplane. As mentioned before, when forwarding a packet, a non-proxy destination means it's been sent directly to the ingress leaf. Proxy means we're sending up to the spine for additional lookup. So in this case, if we have a VTEP that's actually cached on the leaf, the actual leaf itself will forward that switch. So, well, actually, not really true. This is kind of confusing, especially to me. But on ingress, we'll derive the EPG, we'll look at the station lookup, we'll examine the policy and the encapsulation. Now, what does bounce mean? So bounce specifically means if I vMotion this VM from one host to another that happens to be on another leaf switch, and that VTEP is cached on on that leaf, when I move it, it'll put a bounce entry in on the physical leaf itself. Locally significant VTEPs are switched by the leaf. If the leaf does not know it, he will go to the proxy lookup on the spine. The spine will look up and find the VTEP interface for that endpoint device. And then what will happen is that the leaf will update its global station table. So the leaf can then forward that traffic without having to go back and forth to the spine the whole time. He'll just still send the traffic to the spine. So IP forwarding of traffic is between VTEPs. Data plane proxy lookups are for, basically they maintain a mapping database of endpoint IDs to VTEP bindings. And those are actually distributed via multicast routes. So there's one of 16 multicast forwarding technologies. So then that way, there are topologies. So we can use for optimization of multicast load balancing and forwarding. So here, this is this is not specifically that hard. A local station table contains addresses of all hosts attached directly to the leaf. The global station table contains a local cache of fabric endpoints that leaf needs to communicate to. Now it pulls that from the spine, okay? And then the proxy station table in the spine contains all addresses of all hosts attached to the physical fabric itself. So when a packet enters the leaf searches the local station table and forwards the frame if there's an entry. If there's not an entry, then it queries its global station table, then forwards it to the destination leaf. If there's no entry in the global station table, the leaf forwards the frame to the spine to perform a proxy lookup. The leaf updates its global station table. Upon detecting the return traffic, it can then perform direct forwarding. So the spine kind of operates like a default gateway. So the APIC is actually not in the path of the traffic. It's just a management entity, but it does actually control the policy. And then the switches actually handle the physical forwarding of the traffic itself. So if we take a look, you've got leaf 1 wants to communicate. He's connected on 10.1.3.11 on port 9. And he wants to communicate to those individual MAC addresses on those other leaves. The spines are going to actually learn those MACs and IPs at the proxy station table. And if 10.1.3.11 wants to talk to 10.1.3.6, he will go up to the spine. The spine will look up its proxy table, determine the VTEP, and then he will provide that hey, this guy's on leaf 2, and I'll update my global station table. And then if we have another one that's actually learned, same process. I will on leaf 5. I will update my global station table to know that this device is talking to a device that I actually have on leaf 1. So endpoint learning learning and lookup. So a discovery of endpoints can be one of the following: APIC statically programs location identity mapping, remember policy resolution and resolution immediacy, VMM programs, DHCP forwarding, ARP, GARP, or RARP learning, or data plane learning. Now the spines do actually communicate to each other using the Council of Oracle protocols. So they're always running on the spine to ensure all spines maintain a consistent copy of endpoint addresses and locations, but the proxy database exists only on the spine. The spine will act as a packet pump and a proxy lookup. So the spine actually knows where EPGs and AEPs and interface selectors are by actually the APIC provides those policies and then communicates them to the physical leaves themselves. So data plane learning creates mapping at the leaf. DHCP forwarding can be used to learn the mapping entry as well. And we've talked ARP, GARP, VMM, and APIC statically programs the mapping. And all the databases is shared by COOP. So this diagram walks through unicast forwarding in the ACI fabric and illustrates VXLAN header manipulation in the process. VTEP header changes, ingress to egress encapsulation. Okay, so we'll just walk through this pretty quickly. Packet source from VM is attached to the ingress port group or directly from a physical server. It is then encapsulated and forwards it to the leaf VTEP. So here we've got virtual machine to a vSwitch. The leaf swaps the ingress encapsulation with VXLAN. Then if the leaf has learned the inner IP to egress VTEP binding, it will set the required VTEP address and forward directly to the egress leaf. Now, step 4B forwards to the spine for a proxy lookup. It employs an anycast VTEP header. So an example of forwarding a packet from a VMware vSwitch to a Microsoft vSwitch. So the Microsoft endpoint employs 802.1q. So the next step will show where the correct encapsulation is applied. Now, this wouldn't usually happen if you were going vSwitch to vSwitch, but this is just to show you what actually physically happens. So if I'm going to a vSwitch on Microsoft side, my egress leaf will swap the outer VXLAN and it'll correct any egress encapsulation Since this is using 802.1q, it'll then set up any policy there. Then the leaf will forward the frame or vSwitch directly to the physical server, and then the packet is transmitted on the switch port. Now, the operational tab is equivalent of show interface brief or show zone set active in an NDS switch. It's also equivalent to UCSM equipped servers or any verification or command tool. There's two learning sources, VMM, which is vCenter, and learned, that's the endpoint sourced a frame or a packet. Now I can SSH to any APIC to view my bridge domains. So here you can actually see, now this is going to be your biggest friend. You're going to go to Application EPGs, Database, you're going to select the Operational tab and choose Client Endpoints. So you can actually see my endpoint group, the MAC address has been learned, the IP, the hosting server, and the interface, as well as encapsulation and further information as well. You can SSH, and you can do some SSH commands as well to actually find this information. You can also do it in REST as well. So a day in the life of a multicast packet, again, we've got FTAG routes on spines with 16 possible paths. The spine switches maintain a multicast IP overlay group to leaf binding. So a leaf will receive traffic for the IP overlay group. So if an EPG bridge domain exists on that leaf. So the GIPO represents a multicast TEP. So you can see here the multicast frame is received from a server. It's attached to a unique bridge domain and on VXLAN or VLAN segment or port. The traffic is then attached. Destinations are replicated locally. So in this case, we've got two VMs talking on the same physical leaf switch. So, but we're still using the multicast ID, but it's just being switched locally. Now, if we do not know where that destination is, or it's on a remote leaf, the ingress leaf will map the multicast traffic to a GIPO and hashes that flow to a forwarding tag tree. The spine will then replicate and forward the frame to the leaf based on the GIPO address. The leaf will then replicate to all downstream servers and vSwitches. And then the multicast frame is received from a server when attached to the unique EPG bridge domain. All leaf nodes have multiple equal cross routes to all other leaf nodes across all fabric paths. On loss of fabric link, leaf node removes the entry for that link and hardware hashes subsequent frames across remaining paths. The spines will forward all subsequent traffic to any remaining leaves on detection of direct path loss to the target tunnel endpoint address. So on the loss of a fabric link, the leaf node removes the entry for that link and hardware hashes subsequent frames across. The spine will forward traffic to any remaining leaves on detection of direct path loss to the target TEP. The leaf will forward along any valid path to target TEP from the list of valid paths, and ISIS will eventually remove routed to spine with the failed downlink. The ACI fabric does not invoke broadcasts in the fabric. ACI will take the ARP broadcast, query the ARP header for the requested IP, and then perform a VTEP lookup for that IP and perform a unicast forwarding. So that's there's no flooding of ARP traffic. So I don't have 6 leaves constantly flooding to ARP out and go, hey, who am I? Where am I here? That's all done via unicast to the actual spine proxy. So there's your ARP payload, and that's what that actual payload looks like. So if I move a virtual machine over to another host that's connected onto another leaf switch, a bounce entry is created. Bounce means the leaf forward, the leaf no longer has that endpoint, so the leaf will forward that traffic to the spine. The spine will forward the packet to the correct leaf. The ACI capable fabric will then take care of that with no specific routing or switching tasks or configurations. So we're just doing, again, the policy moves with the actual virtual machine. A gratuitous ARP source and destination IP are both set to the IP of the machine, so it'll send all Fs. No reply packet will occur. The gratuitous ARP is a reply to which no request has been made. So as you can see, the virtual machine moves. So if I have other virtual machines that need to talk to that virtual machine that was on leaf 2 but is now on leaf 5, the new leaf will forward the GARP to the leaf where the VM originally was attached. The original leaf installs the bounce entry. Forwarding exception bit in the VXLAN header prevents any looping of those frames. The bounce entry will then age out. Other leaves learn the new source of the VTEP and then update their global station tables. So ACI is also a clause fabric, so there's deterministic latency. So in this case, this is flow-led switching. We want to remove the elephant in the mouse. So we don't want to have large flows supplant small flows. So this topology allows us to hash flows amongst 5 tuples so we can prevent reordering TCP packets. So there's no packet reordering. So ACI can take a flow and disperse it across multiple links. Time synchronization, which NTP is very important, prevents out-of-order delivery. So as you can see here, we've got a large flow and a small flow, and you can see how how those flows are distributed amongst the fabric using ECMP. So ACI will clock the big flows, so that leaves gaps to fit small flows in between. So interleaving flows provides more efficient use of links. So generally, it's 20 to 35% better performance in a steady state. So you can see large flows impact the performance of small flows, so we just slot those small flows in the large flow traffic. So the fabric will detect each flows or flowlets, and the fabric will automatically assign higher flows to small flows. So in the EX and FX switches, there are new troubleshooting tools to measure fabric latency, leverages precision time protocol to synchronize all nodes in the fabric. There's 2 types of latency measurements, ongoing and on-demand. Ongoing measures latency across TEPs, and on-demand is configured by the tenant to troubleshoot issues at the level of individual applications. And that is Module 1.